All right, so sigma notation, huh? One of those things we're going to have to get into soon enough. So this is sigma notation. This is the sigma in Greek. And typically you'll have a letter like I at the bottom, and you'll have a number up top, like 4 or something. And then you'll have some kind of function right here, some kind of an equation. Well, not an equation, an expression. So like 2i plus 3. So what does this mean? This means to start with this number and plug it in. So 2 times 1 plus 3 gives me 2 plus 3, 5. To that, add the next number. So I call this right here the index. You're going to increase the index by 1 to 2 and plug 2 in. So 2 times 2 plus 3, which gives me 4 plus 3, 7. And you're going to add that to your first answer, which we'll do at the very end. Then you increase the index by 1 more and keep going. So 2 times 3 plus 3, which gives you 9. And one more time, because the top number tells you where to stop. So the top number tells you when to stop adding. So 2 times 4 plus 3. And that gives me 11. Add them all up. 11 plus 9 is 27, 32. So this summation equals 32. So it's called a summation because you are summing basically variations together. You're indexing. So if you're taking computer programming or computer science, you usually have like an n plus 1. That's what this is doing. It's adding 1 to the index and then you're plugging it in. So that's how summations work. Okay, so in second semester, we deal a lot with summations like this. Okay, so obviously that kind of starts to lend itself to why an integral works the way it does. You're summing up infinitely skinny areas under the curve to get the total area. So there is a way to link area under the curve to this idea of summing up infinitely skinny rectangles. Okay, so that's what a sigma notation is. Part 1 done. Part 2, I need to prove something to you. I need to prove that I equals 1 to n, wherever I put n to be, of I equals n times n plus 1 over 2. Okay, so again, this goes back to my love. I already talked to you about this. My love of mathematical proofs and showing that one thing equals something else. This is a generic proof that says it works for any number. So for example, here's what it's saying. It's saying if I have this, I equals 1 to 5 of I. Well, when it's only 5, it's easy to evaluate. This is the same as plug in 1 plus increase the index by 1, so plug in 2, increase the index plus plug in 3, plug in 4, plug in 5. That equals 6, 10, 15. So the proof is saying that if once we prove it, that I can also just plug in, if this is what n is in the problem, it should be the same thing as if I plug 5 into that right side of the equation. So 5 times 5 plus 1 over 2. Let's see. 5 times 6 is 30, divided by 2 is 15. So yeah, it appears like this identity is true. So this is otherwise known as an identity, when one thing is equal to another. It seems like this is true. And you can kind of just take it and run with it again. If you're like, oh, cool, it looks like it works, it works. It could be a coincidence. I mean, you could test it for 40 different values of n and see that it's true. But we're not going to do that. We're actually going to prove it. So we don't need to test it by brute force. We can actually do the proof and know that it's true. Okay, so here's the proof. Here's how you're going to start it. You know something. I plus 1 squared is I squared plus 2i plus 1, right? If I multiplied it all out, FOIL, I would get this. I'm going to move the I squared over to the other side. So I plus 1 squared minus I squared equals 2i plus 1. This is an equation, meaning I can do the same thing to both sides, and it doesn't change the fact that it's an equation, that it's still equal. So I'm going to take the summation of both sides from I equals 1 to some unknown n. Okay, I could do it just like our example and put a 5 in there, but I want to keep this general. So as long as I keep it general on both sides, we're fine. Because if we started out with an equality, something that's true, so everything I do to one side, I do to the other, everything is good. Okay, so I'm summing across on both sides. Okay. A thing that you are not going to know, and one of those things that you're going to have to kind of confirm for yourself, it's kind of like integrals. If I had the integral of x squared plus 4, I can split that integral into integral of x squared plus the integral of 4. Sigmas work the same way. Sigma notation and summations work the same way. So I am going to split this up into 2 sigmas that I can then add together. Intuitively, that should make sense. If sigma is just about adding and adding, we can split it up and then just add after. All right. So we're going to split up this side. This is something interesting happening on this side. And this is a big deal. This is going to be a big thing second semester. The left side looks like a mess. Let's just try plugging numbers in and see what happens. So I'm going to plug in I values and see what's going on. And you'll see something pretty cool. Ready? So I'm going to plug in. I'm going to start with 1. I'm going to plug 1 into this. I get 1 plus 1, which is 2, which is 2 squared is 4, minus 1 squared is 1. I'm going to keep it just like that. I'm not even going to simplify it. I'm going to keep it separate. Plus, let's plug in 2 now. 2 plus 1 is 3. 3 squared is 9. Minus, plug in 2, you get 4. Plus, let's plug in 3. 3 plugged in, it gives me 4 squared, which is 16, minus 3 squared is 9. Plus, the next one's going to be 25 minus 16. Plus, on and on and on. Do you notice something going on? Look, we have a minus 4 plus 4, minus 9 plus 9, minus 16 plus 16. All of the middle terms are canceling out. All we're left with is the first term, minus 1, and quote unquote the last term. In this case, I just plugged in 4 to get this. So I plugged 4 in and got this term. Notice what I'm left with. That's 5 squared. So you're left with n plus 1 squared. So you're left with n plus 1 squared minus 1. That's probably the hardest part of this whole proof right there. So you may want to go back and try to understand what I just said. You start plugging in I values, all the middle terms cancel. The terms you're left with are this minus 1, and you're left with the last term that doesn't get to cancel, and it is 1 bigger than where you stopped. So I stopped at 4 in our example here, and I was left with 5 squared. So whatever n is, you stop with n plus 1, the term bigger. And now we've simplified the left. It no longer has a summation anymore. Equals. So we are at, I'll rewrite it. Let me rewrite it cleaner. So on the left, we have n plus 1 squared minus 1 equals. On the right, we have this first summation that's not going anywhere. Plus, well, what's going on with this summation? We're summing together a bunch of 1s. Let's try the same strategy of just plugging in and see what happens. If I plug in 1, the output is 1. Plus, if I plug in 2, the output is 1. If I plug in 3, the output is 1. If I plug in 4, the output is 1. All the way up to the last one, which is the nth one. So how many 1s do I have? Well, if I stopped at 7, I would have 7 1s. If I stopped at 8, I would have 8 1s. If I stop at n, I have n 1s. So really, this is 1 plus 1 plus 1 all the way up to n. So this term equals n. Okay. Now we're almost there. I'm going to multiply out the left, so I get n squared plus 2n plus 1 minus 1 equals. Sigmas are just like integrals, like I said, so coefficients you can move out front, just like we've been doing. Just like we've been doing with integrals. So you can move coefficients out front too. And then look what we can do. Cancel, cancel. I'm going to subtract this over. So I have n squared plus n. I can divide both sides by 2. And what am I left with? This right here equals, and I can factor out an n. And that's that identity we were trying to establish from the very beginning. N times n plus 1 over 2 equals the summation of I from 1 to n. Okay. So you may have to go back and watch that a little bit. It's only a 10-minute video. It's not bad. I love proofs. This is where my mind likes to go. This is like a puzzle to me. You just have to replicate it for the discussion, and it doesn't come up in this class. Things that do come up is this idea right here, where you're summing together n number of ones. This type of thing right here, where these terms canceled out, this is called a telescoping series. This is going to come up. So telescoping series, you'll see again second semester. So it's kind of cool that you get to see one right now. And then this whole idea of how a sigma notation works with an index and a stopping point and all this stuff. Okay, so that's part one. There are 3 parts to all of this to show how the area under the curve is equal to an infinite summation. And I think it's worth seeing. We have time in these discussions, so I don't mind. While we're doing accumulation in the rest of the class, it makes sense to kind of do this right now. All right, that's it.